those in video land, you just missed, quite a bit. You kind of did, right? I hope that was helpful. And, okay, so remind you where we were at last time. Last Friday, I know, was extremely painful. That was 2 full hours of lecture, where the main point was to start out with was talking about how, I'm going to talk about something A, and in the mixed state, or whatever A is, methane, ammonia, water, I don't know. You have the number in the table in the back of the book, which remember is a formation, delta G, but that's okay as long as every number I use comes from a table in the back of the book, which are all formation G's. Normally I would say this would just be the absolute quantity, just like you figured out what U was for argon versus N2 versus CH4, and that degrees of freedom just mattered, how that, what it was, you calculated heat capacity, and, you can figure out what U was. Well, you can figure out what G is, but it ends up being too difficult, so we use delta formation G's as stand-ins. Okay, now the point of this was, and here's another way to represent that. To remember that this was how it mixes, and especially with your gases. The point of this was to introduce you to the fact that the number in the table in the back of the book are for pure substances. And as soon as something perturbs that, like we change temperature, don't worry about it. When we perturb that, and in the case of reactions, we have to mix them, then this number, the table in the back of the book is a starting point, but we have to change it based on this. So the number in the table in the back of the book are for pure substances, that no reaction can occur that way, right? All right, so then what we go from there, I showed you how to derive that, and it was kind of long and painful. This was the end result, so you don't have to worry about necessarily deriving it, but I do want you to see where things come from. Okay, then we talked about entropy, where am I at? We talked about entropy, which I think is a question on the homework, but kind of easy, so I'll just drop that. The next thing we talked about was reactions, okay, so notice I don't have a little subscript because I'm not talking about pure substances, and, or how do I want to put this? Let's do the example of A plus B goes to C plus D, which is as complex as something as I could reasonably come up with. Obviously, this just gets more simple if I just go A goes to D, and I'm going to do that today. What you have is the Hess's law question, which, again, chemical potentials are, doing my symbols wrong. I'm really off today. It's a lot of stuff I have to cover today. Now I'm being just OCD. Okay, remember that a chemical potential is a G per mole, but look at the table in the back of the book and you'll see that the G's are per mole. Those are actually chemical potentials. So this again is just your high school Hess's law. And again, what I introduced you to was the idea that this is perturbed in the reaction due to mixing. And it works this way. Again, an ultra long derivation, took me nearly an hour just to get to this. And the big picture was that when I started this out talking about how the number in the table in the back of the book, I can say that quickly now, how that number is perturbed by mixing, and mixing has to happen before things react. But that was really just done just to get you, like, yeah, okay, of course I get that. Oh, of course you mix first. Of course the delta G changes, and then products minus reactants. Then this term shows up in addition to this guy here. I'm just trying to get you to follow along, whereas really only this is the only part that matters, but let me even go further with that. Note that since G is a state function, I didn't need to do any of this. I never even had to get you to think about mixing. I never had to get you to think about, well, okay, now it mixes and it starts reacting, that's here. I never had to do that. I can just go to the endpoint. State functions, right? It doesn't matter how you got there, it just matters the end. The end I care about is that when the reaction is done. because that's when I'll be able to count up the number of products over reactants. In other words, I know the extent of the reaction. In other words, I know the reaction yield, which as a chemist is all you could ever humanly care about. I mean, it's interesting from a just curiosity standpoint to understand how reactions are going forward. And I mean, I was personally, I studied kinetics as a graduate student, but from a chemical industry, which is what a lot of you will end up doing, you really only care about how many products you made, in which case this guy goes to 0, and I'm going to cover that in a minute. But anyway, that's just kind of the big picture of what I covered last time. And let's see. Now, graphically, let me do this. Remember I told you that for the most part, you're going to want to study things where the Hess's law goes downhill, where the products have less chemical potential. So I need to put that per mole, because only per mole matters. The products have less chemical potential than the reactants. That's good, right? But remember that the effect of this entropy part, which we began with mixing, but then as things react, they continue to mix. That is why you may see a reaction not go to equilibrium, and this will be reactants, products. So this might be, I just misspelled products. This might be, let's say A goes to B, this would be the mole fraction of B then, so for A goes to B, if this was the reaction, because there's 0, B for the reactants and 1 for the product. Anyway, I'm just being all hypothetical, hopefully you can follow along, but anyway, blah, 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 blah. Okay. High school says the reaction goes forward, college says, but not all the way. Right. And this Boeing is this term right here. That's where that comes from. Other things you might expect, say, on Friday is, remember I was telling you that this explains, it explains why reactions don't go to completion, which is nice and useful to know that. I also mentioned, oh look how OCD I am today, something's wrong with me. And I'll just stick with this A goes to B idea. Now, not all reactions are favorable. Some go uphill from the table in the back of the book. But again, mixing may mean that actually it is favored, because note that as A goes to B, A is getting to mix with B and B mixes with A. And that's always good, that's always entropically favored. Pure A, even though A, according to the table in the back of the book, doesn't want to form B, it does want to mix with B. And so the two battle it out, probably not in B's favor, but it also means the reaction doesn't not go at all, right? And so what you're going to cover today is where this thing dips out. You're going to locate it and then know exactly where, exactly how much, you're going to know your reaction yield. And we're going to do gas phase reactions, because if I can't do gas phase, I can't do proteins and drugs and all that, so why bother? Now actually notice that almost any reaction will go to some extent due to mixing. Because even if you have an entropically unfavorable reaction, like lots of reactants turning into one product, that is bad because that's overall entropically lossy. However, even if you have a lot of products in one reactant, a lot of reactants in one product, the formation of that product gives you one more thing to mix with, which again is always favorable, just probably not to a large extent. Let's see. One thing so actually let me go ahead and start on the material at hand, which is, again, let's forget about how we got there, because we don't need to consider how we got there when we're talking about state functions. Let's talk about where we ended up, which is I really didn't express this very well. I should have done it this way. I should have expressed it as this extent of reaction. That's what I meant to do. And again, point out to you, this is how I did it last time, I just forgot. Point out that what we're looking for is this. we're looking for this, which is then equal to the number in the table in the back of the book, plus this entropy part. And I'm going to use a new symbol here because it makes my life a lot easier. And hopefully you should have seen this little symbol in high school. Maybe you haven't. How many have seen that symbology before? Pi. Yeah, have you seen that before? Left side that never says anything. It's not pi, it's not 3.14. That doesn't make any sense. No? Yeah, wait, seriously, have you not seen this before? Okay, that's really bad. I saw this in high school. All right. Pi is a multiplication. It's, and you guys gotta ask me this stuff. Pi is, sorry, I don't know why my handwriting's all up today. All up to date. God, something really wrong with me. Pi is to multiplication as sigma is to addition. Right, so it's a bunch of things multiplied, just like big sigma means a bunch of things added. So, wow, you should have seen that. Nah, it's not my fault. I'm trying to put you down, putting your teachers down. They should have shown you this by now. Anyway, this is what I like about the symbology is it's a little easier on my wrist. Number two, it emphasizes that the stoichiometric coefficient of, in this case, let me jump up here, of products of, God, what is wrong with me? Reactance is negative and products is zero, which is how you get this whole equilibrium constant of products over reactants, right? Because the product stoichiometric coefficient are positive and the reactants are negative. Yes, I did say that right. Okay. All right, so therefore, again, we're cutting to the end. Therefore, minus delta reaction G naught per mole, again the number of the table in the back of the book, over RT is the natural log. Again, just remember if you have a little bit of trouble with this, I'm sure that if you need it, it's in the cheat sheet. Again, I'll send that Wednesday. Remember that this is just your equilibrium constant. Just remember what we showed you in high school where it was a ratio of concentrations. It was actually incorrect. And the funny thing about that is that actually I was looking through when I taught this class the first time, I looked through your freshman chemistry textbook, and I saw that they actually always picked examples of A to B or AB goes to CD. In other words, they always made certain that the units canceled. They never gave you one where like A goes to B and C, where you would have a net unit, a natural log of a molarity, which would be impossible. They always biased it towards that not happening. You didn't notice that because why would you have, right? Okay, so, and another thing, note that since we're doing gas phase, again, because if you can't do that, then what the heck? We're going to put things in terms of the partial pressure after the reaction divided by the initial partial pressure. I will define the initial partial pressure as P naught, which is 1 bar. Okay, two reasons for that. One is if that part, just you forget that part, although I'm going to drill it into you by the end of the day pretty hard. If you forget that the mole fraction isn't a ratio of pressures, that if you just think it's the partial pressure, you will have failed to divide by 1. So you won't have screwed anything up. Especially if I give you the answer, you'll still get the answer. I will barely take off points for that, if any points. Number two, actually, you have to do this. You have to put the initial, what if the initial pressure is not 1 bar? No, you have to do it that way. It's because this guy is in here, and this guy is here, and this is the number that, from the table in the back of the book at STP. What's the standard pressure?
1 bar.
Yes, right. So the initial pressure, when everything's unmixed, and this guy gets you away from that, it takes into account the mixing as the reaction occurs. This was done with everything by themselves at 1 bar. So your initial pressure, by definition, must be 1 bar. Now here's the neat thing. Now obviously all the numbers in the table in the back of the book were measured, But some things you can imagine that you have numbers for gases that you couldn't really create at high pressure for some reason. Like they're very low vapor pressure, like water. How would you get a mole of water vapor at STP? How could you do that? And I mean 1 bar, one atmosphere, slightly less than 1 atmosphere of pressure of water vapor to measure the G. How could you do that? Or could you? Huh?
You can't.
You can't. If you have a box, even if it's a vacuum, and you start adding water, once the pressure rises above a certain level, and I believe I actually know the number offhand, 600 pascals, because I'm just like that, it will actually start to liquefy, and there's no avoiding that. So what they do is, that number in the table in the back of the book for gaseous water at STP was measured at a lower pressure because you have no choice about that. At higher pressure, the 1 bar that the number is written for, you wouldn't have gaseous water, you couldn't make the measurement. What they do is they make the measurement under conditions that they can. What choice do they have? But then the number in the table in the back of the book gets fixed after the fact such that it's the correct number for 1 bar of gaseous water, even though you cannot have 1 bar of gaseous water. And it's like, well, why did they do that? Well, because when you calculate a reaction yield with water in it, the number is correct. If they didn't do that, the numbers would be wrong. So that's why they did it. I think it's kind of obvious. How did they do that? I'm actually going to show you next week. Let's not worry about it right now. Okay. And so remember that this is what we refer to as K, which is a what is this? Equilibrium constants. Now, technically, I'm going to just barely touch on this. If the reaction, just to remind you of your freshman chemistry, that if the reaction wasn't at equilibrium, you call this Q. Do you remember that? It was called Q if the reaction hadn't gone to completion, and K if the reaction was in equilibrium. Just to remind you, I'm not talking about, I only care about equilibrium because why wouldn't I? Okay, now there's some funny things about K I have to come over, and then I'm going to show you how to actually calculate a reaction yield of, I think I'm going to actually do the example of the homework. You're just going to plug in numbers, and as I subtly reminded you, Friday or Wednesday, you've actually already done the numerical calculation in the previous homework. Don't worry about that if you don't remember. It doesn't matter. Okay, there's some quirks about K. One is K is pressure independent. Okay, now why is this important? If we do an example, and I will do an example today, where the number of moles of gas changes, it's reasonable to expect the pressure to change, the net pressure. So we'll worry about the partial pressures in a minute. You'll see that in a second. But here's my point. If I have a chemical reaction that produces gas, 1 gas turns to 2 gases, it is reasonable that although we start at 1 bar, the pressure will rise. If that affects K, I've got a problem. Now, it just may be like a problem like I had with delta A and delta G under adiabatic conditions where, yes, it can be calculated, but it's complicated and I need a computer. It could be like that, but it's not because the K is actually pressure independent. So if I give you K, like I think I did on the homework, it applies to any pressure. And okay, there's 2 things about that. Let me explain why, then let me explain the consequence, which is actually one of the hardest things about this, but it makes sense. I'm going to try it. I will try my best to make it sensible. Okay, so why would K be pressure independent? Well, let me tell you what pressure does. And remember, again, we're sticking with gas phase. And I'm going to use the example of a gas turning into 2 gases, because again, I said this is where it gets funky, right? But, otherwise it doesn't make a lot of sense. Okay, let me show you what pressure does. And let's look at energy. All right, remember these are, hopefully you've seen this before. I actually showed you one of these, a potential energy surface, when we talked about why gases are real gas behavior. I showed you a potential energy surface. And we have reactants on the left and products on the right. That would be 2B on the right and A on the left. And this is, again, our extent of reaction. And we expect the reactants to be stable. There's a barrier to form products. And I'll make this nice and symmetric. There's no reason it has to be. Anyway. Okay, let me show you what pressure does. By the way, this is part of PChem Lab, depending on who teaches it. We have a module that does this. Okay, now you know that A has to gain energy to get over the barrier. Now, in your PChem lab, you actually give a reaction enough energy to go over the barrier with a flash camera. Obviously, it absorbs light, and that's energy. In the case of a gas-phase reaction, what happens is that something else, another gas molecule, comes over and hits it. It's a collision. Collisions wouldn't happen unless there was some pressure, and more collisions occur with higher pressure, right? Okay, so that gives it enough energy, right? So there's a certain finite amount of energy, and now it has enough energy to go over the barrier, and now you've got 2B molecules, right? So the reaction has occurred. All right, so it looks to me like pressure should actually increase K. Remember, K is products over reactants, right? And it looks to me like pressurizing physically gave A enough energy to form B. Therefore, I have more products and less reactants. K is products over reactants. K just got bigger. Notice I just said it should. Okay, now here's the funny thing. Conservation of energy. What do you think the 2B molecules, what do you think the 2B molecules can do right now? They can what? Just turn right back around, right? Conservation of energy. They just turn right back around and form A. Why wouldn't they, right? They have, if you have enough barrier to go, enough energy to go over the barrier, you have enough energy to do it again, the other way, right? And what happens is, so why does anything occur? Well, that same gas molecule, not necessarily the same gas molecule, you get my point, would actually get struck by the 2Bs or the 1A, and then dump you back down, here or here. Okay, so again, let me walk you through this. I know this got complicated, unfortunately. A gas molecule struck A, gave it enough energy to form 2Bs, but they have enough energy to go back. Now, they'll form products if they shed their energy by hitting something else, and that maybe, just like energy was given, it can be taken away, and now you form two products. That's why you get products. But notice that unless that happens, you go backward and form A, in which case the same thing can happen at this point, which is that the energy gets dumped out of the system, again by collision, and now you've gone nowhere, right? The whole point is that there's no telling how this happens. Right, which is my point. There's no telling how this happens, so you don't really favor products or reactants by changing the pressure. And another big point of this is that it is part of PChem Lab, so I'm trying to help you out there. Okay, now this is where this gets really freaking nuts. Your interpretation, if you're a normal person, is that pressurizing, in this case, changing the pressure would therefore do nothing to the products versus reactants to keep K constant. Again, K is constant. That is not correct. Okay, this is nuts, I swear to God, but here's how it works. The reaction, balance, sorry, I should have done it this way. Right, we're at equilibrium. The balance of products and reactants actually does change with pressure. It actually does respond such as to keep K constant. Okay, now I'm going to do that mathematically because right now I don't think you should be able to see that, so I'm going to do this, but I just want to let this sink in. K is pressure independent, so therefore if I'm monkeying up the pressure of this reaction, there will be a response. But the response ultimately does exactly what I just said. It keeps K constant, and I will show you that mathematically. Now let's define what K is. K in this case will be the pressure of B squared. Okay, so the stoichiometric coefficient is 2, and A is on bottom because the stoichiometric coefficient is 1. true and false question, and I just missed it. What's the stoichiometric coefficient of A? If it was 1, this would be PB squared PA. It's -1, right? It's a reactant. It's -1. Okay, so this is the reaction quotient. Okay. Now, if pressure goes higher, then both of these. Well, what I would do is, sorry, let me make this more real so it's more sensible. If this occurs in a box, what I'm doing is I am compressing the box. It's like an accordion or something. I don't know, weird box, whatever. If I do that, the partial pressure of B would rise. But K is constant. So what does the partial pressure of A do? Now remember, it's in an accordion, right? It what? Does it go down?
Yeah.
Don't be snide. All right, partial pressures. I'm crushing the box. This went up. What did this do? Goes up. Look, I just described the pressure of a gas as the volume decreases. The pressure goes up. Of course the pressure goes up. Jeez, folks, this is 5th grade. I just asked you a 5th grade question. What happens to pressure in a box when you crush it? It goes up. Okay, now here's the college level. Remembering that this is constant, does this go up as much as that? Yes, it goes up as much as this. This is constant. If this doubles, this doubles. Okay, now let's be a little bit more careful about this. Let's say PB, let's crush it by half. The partial pressure of B has doubled. What does this term on top do then? 2. Okay, the partial pressure doubled. What does 2 squared equal? 4. Okay, what does the partial pressure of A do? Quadruples. All right, did you see that? I doubled the partial pressure of B, but that means that the partial pressure of A quadrupled. Right? Now, how would you do that? How would that occur? Now, I've got this balanced equilibrium. How am I going to drive up the partial pressure of A twice as much as B? Now remember, B doubled because I crushed it. I have the volume. The partial pressure of B has to go up. And let's say it's about a factor of 2. The partial pressure of A goes up because, again, I'm crushing it. But it has to find a way to go up even more. By, in fact, another factor of 2. How am I going to do that? Think of this equilibrium. Does the equilibrium get perturbed?
Does that shift to the left?
Yeah, it shifts to the left. Folks, pressure is proportional to moles, right? If A has to increase its pressure, you need more A. There's no other option because they're in the same box. Again, the same box was crushed by half. That drove up this guy's partial pressure by 2. But this K thing means it's got a factor of 4 that A has to deal with. The only way to drive up A, now remember, I doubled A's pressure just like I doubled B's. But it's got another factor of 2, and the only way to do that is to increase the number of moles. And that means the equilibrium shifts to the left. All right, now again, that's a mathematical proof that the gas phase equilibrium does respond to pressure, but it does so to keep K irresponsive to pressure. Why is that? This reason I just showed, which I'm not going to, that's kind of like graduate school level understanding that this is the case. Anyway, and you'll see a little bit of this in PChem lab. But yeah, okay, now there's a whole other way to explain this. Now, if you're trying to memorize this for the exam, again, this will be exam 3 or the final, so don't worry about it for exam 2. But if you're trying to memorize it, let me give you a really easy way to remember this. Le Chatelier's principle. Now, I'm talking about adding pressure. So think of this as Le Chatelier's principle. Which side of this equilibrium could you call pressure pressure is a product or a reactant? It's a product, right? Because you're making more gas, right? You're increasing pressure. Pressure is a product. If I add more pressure, do I get more reactants or products? Reactants. Reactants. Remember, remember Le Chatelier's principle. A stress to the system is relieved. The system tries to relieve stress. If a system has too many products, it will go backward and form reactants. Pressure is just is a product, right? So again, pressure is a product. There's a stress by adding more product. It responds by forming more reactants, and vice versa, right? If I had done 2A goes to B. All right. So anyway, that's the best I can do with that. Let me do 2 examples, and then that'll be it. One is I'm going to do this in more in depth. But I'm going to do it with a real system because this is a little too abstract for my liking. Plus, one thing that kind of drives me nuts is that sometimes with all the classes I've taken, we often see a really simple explanation. This is as simple as I can get it, and then you're given a real system or more realistic system as a question. And there's some like weirdness to it, a little extra that you didn't see, and now you're like, well, hold on, we didn't cover what happens when there's half a mole, blah, blah, blah. Okay, so that's why I want to do it this way, and again, so a real system, and one of my favorites is, I don't really have a biological gas phase example. I wish I could, I've looked for the ones that I could try to come up with, but I just never, there just really aren't any that I know of. And forming ammonia is kind of important anyway. And again, we're doing gas phase for all the reasons I just said. And now actually I need to be a little bit more careful with defining the equilibrium constants because I actually left something out, which is that K is, I actually left something out last time. Let's see, I've got to do NH3. Actually, I left out the P naughts. I actually did that last time. And all of these are squared. So this is on top. Now let me do the ones on bottom. And I'm not going to put them underneath. I'm just going to flip the ratio because otherwise it's too painful. Let's see. I've got 1 bar cubed. I'm doing hydrogen. So again, this is 1 over the mole fraction of hydrogen. Again, assuming that its initial partial pressure was 1 bar. Notice that again, remember I told you the 1 bars don't matter. And nitrogen has a stoichiometric coefficient of 1, so I don't do anything other than, sorry, the stoichiometric coefficient is -1, which is why the mole fraction has been flipped, right? Okay, so now what we do is, now this is how you're going to do your homework. And again, so this is chipping away at the homework. I'm going to do this in a bit of an abstract way, and then I'll do the actual homework. But you do use Dalton's law. Dalton's law, which is you assume that the pressure of X, let me not use the letter X, let me use A, is the mole fraction of A times the total pressure. Right. And again, I'm still messing with total pressure here, just to get all this cemented. And then this segues into actually calculating. Let's see, what I'm actually getting to, by the way, just foreshadowing executive summary, is what you're going to do on the next problem and on your homework is you're going to actually figure out what the mole fractions are, and that gives you information on how far the reaction actually occurs. Okay, in this case then, K is, let me not bend over and kill my back. Okay, so I've got NH3, partial pressure of NH3 squared. So I'm just factoring this out to make this a little bit easier. Okay, I've got this. So anyway, I just wanted to factor this to make this a little bit easier. Okay, now I've got the mole. Now I'm inserting Dalton's law. I've got the mole fraction of NH3, and that is of course squared. By the way, I'm writing this in such a way as to, I'm just factoring out the pressures, you're just not seeing it yet. I got the mole fraction of H2 cubed. I got the mole fraction of N2 on bottom. Now, for each one of these, I pick up a factor of pressure 1, 2, 3, 4, add the factor of net pressure squared. And all of this balances, by the way. Let's see, I've got pressure squared, pressure to the fourth, And again, if I was careful with my 1 bars, I would have a 1 bar squared on top. Not that it matters, it's the number 1. Okay, now let me factor all this into mole fractions, and this again is 6th grade algebra. I'm just going to come up with a statement that's in pure mole fractions. Okay, pure mole fractions. And then I've got something that doesn't matter ever because it's the number 1 over p squared. And let me show you how the book tends to represent this. You have like a mole fraction component. There's a K that you can describe in mole fractions and another part that's due to pressure. Okay, so that's how you do it. Okay, now again, what I want to emphasize is that what I'm about to do in the next example is figure out what K is and then solve for the mole fractions. And again, that tells you how much the reaction goes. Now, for the purposes right now, what I want to point out is I've got to look at this and where is my pressure in terms of is pressure a reactant or a product in here? It's a reactant, right? There's more gas on the left and less on the right. Now let's look at this. If pressure goes up, what does this guy do? This thing goes up or down, right? Okay. In which case this thing goes up, right? Okay. So if this goes up, that means you have to have more ammonia and less yada yada yada. Okay. So pressure favors ammonia. Now let's look back at this. If pressure's a reactant, adding more reactants makes more product, which is ammonia, and that part goes up. Right, totally makes sense. So, yeah, that's really all I want to do. And then I'm going to do one more example of water, which again is the homework example. And again, this is just a way to help you set this up. But let me go ahead and do water because this is the same idea. You know, like I say, I'm just segueing into water. I just want to use this as an example to mathematically get across how equilibrium is affected by pressure. And by the way, what I'm going to do is we're going to figure out what the extent of water reacting is. And then you can even prove Le Chatelier's principle. That's something you'll do on the next homework if I'm not mistaken. Anyway, here, let me actually write out the examples and I'll give you an idea of what I'm going to ask you to do. But we won't worry about that for the next test. So anyway, what I'm doing now might be on the 3rd test. So I said water reacting, this is what I meant. Because this is kind of important, right? This is how we get water. And so now I'm going to show you how to figure out, I'm going to give you thermochemical data, numbers in the table in the back of the book, and you tell me exactly how much of what. And we'll do this at like STP, right? We can mess with that, but we won't. That's too hard. Okay, the way to do this is you start with something we call alpha, which is what I'm going to call the extent of reaction. So it's kind of like so I'm kind of screwing up here. I just realized that. I was calling that epsilon before, but for various reasons I'm going to rename it. I'm going to give it a different Greek letter. I just kind of realized I was just changing that definition, so I feel kind of bad about that. Anyway, let's see. Okay, we're going to start with N moles of H2O. Okay. Now, what I'm doing, by the way, executive summary, I'm trying to build an equation for mole fraction that I'm then going to equal to the K that I get from the numbers in the table at the back of the book. Okay, therefore, as this reaction proceeds, so what I have to do is I have to phenomenologically come up with a model for the number of moles of water as the reaction occurs. I start with N, and if this reaction goes to completion, there should be 0. So this is pretty easy to figure out. What I do is subtract alpha n. Right, so the point again is to model the number of moles of water as the reaction occurs, a phenomenological model. But this is correct unless you can split an atom in two. Okay, you can do that, but you definitely shouldn't. So yeah, this just totally makes sense. If there's no reaction, I still have my original 1 mole. And if the reaction has gone to completion, I've got 1 minus 1, or 0 moles of water. Now you can figure out how much, let's see how much H2, how many moles of that would be alpha N. And O2 would be 1/2 alpha N. Right, because if the reaction goes to completion, I've lost 1 mole of water, but I've gained 1 mole of hydrogen, and I would have gained 1/2 a mole of oxygen. Now, mole fractions, right? Therefore, the total number of moles, which then we're going to get the mole fraction from by dividing, the mole fraction of water will be this divided by the total, and my mole fraction of H2 will be this divided by the total, and that divided by the total, so let's figure out what the total is. Which, this is brainless, by the way. Just add them all up. N minus alpha N, that's water. Here's the amount of hydrogen. Here's the amount of oxygen. You see how easy this is? See, now I've got formulas for the mole fractions, and this is 1 plus alpha over 2 times N. See, it's really not hard. Really, I can straight ones, all right. Really not hard at all. Not hard at all to do this. And this is a relatively complex example. I probably would do something similar like A goes to B on an exam. Third exam or final, not this one, right? Okay, now with this, what I want to do is figure out the bits inside of the K, and that is the mole fraction. Let me do mole fractions, and then I'll insert them into the equilibrium constant. And, okay, let me do water. In which case, the number of moles, which is 1 minus alpha over N, divided by the total, which is 1 plus 1/2 alpha. And you see how easy this is. This is 1 minus alpha over 1 plus alpha over 2. And therefore, the mole fraction of water times the pressure is the partial pressure at H2O. Right. And this is the mole fraction. Sorry, I screwed that up, didn't I? This is the mole fraction. So you multiply this mole fraction times the total pressure, now you got the partial pressure, which is what goes into decay. Okay, let's do H2, which is alpha N over 1 plus alpha over 2N. Which is alpha over 1. You see, by the way, when you do this right, this of course is the mole fraction of H2, and therefore the mole fraction times the total pressure is the partial pressure, which is in the formula for the equilibrium constant. And let's do O2. Which is a little bit more complex. 1/2 alpha N. Okay, so if you want to just maybe sit back. Actually, you know what I can do? I'm actually going to simplify this. I'm going to multiply the bottom by 2. 2 plus alpha. Which is, of course, the mole fraction of O2. And therefore, the mole fraction of O2 times the pressure, total pressure is the partial pressure of O2. Okay, almost done. Now what I want to do is use all this to build the equilibrium constant. And we're home free. You just use a computer to solve it. I'm almost, it's going to, just insert it into the equation and then just point out you have to solve it. Which you do need a computer to do that because you're going to end up with a natural log of this alpha field, and alpha tells you how far the reaction goes. So what I would ask on a test or homework is just tell me what alpha is. If you tell me it's 0.9, then I know the reaction goes to 90% completion. You get the idea. So now K, gotta define K, that's the products divided by 1 bar. I'm just being careful, exact. I don't need to write down 1 bar, by the way, because it doesn't matter. By the way, 1 to the half is still 1. And products over reactants. And now I put this in terms of mole fractions. I had to put all this to the 1/2. That's kind of a pain. You can see why this is going to be a bit of a pain and why you're going to want to use a computer. And then I've got to get my my 1 bars and my actually I think yes, no, I made a mistake here. PO. Not that it matters, I'm just being exact. Okay, now I insert all that jazz. What you get is alpha P times alpha over 2P to the 1/2. And at this point, you're at a middle school level of factoring. You know, I'm sorry that, this is just a necessary evil. Now we've got the last bit. And I'm having to rely on my notes. Mine is almost completely here, by the way. Right, this is H2, O2, and and then this is actually from this guy, right? All right, this makes sense. And I'm going to be exact with my partial pressure. Okay, some factoring done. Do all the factoring. What you get is this, which is really kind of painful, but again, it is a middle school level skill. Did I? Yeah, I got this right. Okay, sorry. I'm kind of rushing here a little bit. Anyway, so sorry about the rush, but this is all just a matter of algebra. And, I hate getting stuck with stuff like this, but this is what we do have to do. And what we'd like to try to do is represent it this way as a mole fraction component and a pressure component. But what I'll do is on the homework, what you do is you just assume that the pressure is 1 bar, and this is 1 bar. And what I've done is I give you the equilibrium constant, which again is like minus delta G. It's e to the delta G over RT, right? Sorry, e to the minus, let me remind myself. So what I've done is, let me just show you where this comes from. What you do is you have Hess's law that gives you this, divided by RT, you use 298, that gives you K. That gives you this guy here, which you then solve for alpha using a computer. And that's how you do it. So I'm sorry for all the mathematical mess and algebra. That's exactly how you do it. Just watch the video again if you're having a little trouble following all this. But that's how you do it. Remember that technically you have actually solved this bloody mess in the previous homework. And good luck with that. Good luck with your test. Remember, comprehensive review wins.